Hello everyone. In today's lecture, we are going to discuss two-dimensional motion under gravity, which is commonly known as projectile motion. So let's begin our discussion. Two-dimensional motion under gravity. Which we generally also which is generally also known as projectile motion. So we have three assumptions to study the projectile motion. Projectile is a common word which we generally use for our day-to-day objects which we come across in our daily life, like throwing a ball in the air, stone, football, and what else. So we have three assumptions which we need in our discussion. The first, we will neglect the air resistance. Second, we will treat our surface as a flat surface. Our surface is flat. And third, acceleration due to gravity G is constant, which is also very much justifiable for our day-to-day objects, because the range of the objects is not so large, so G can be treated as constant. So let us assume we throw a ball with the horizontal surface at an angle theta. This is our point of projection, and u is the velocity with which we throw the ball, and it makes an angle theta with horizontal. So for our analysis, we will consider the horizontal surface as our x-axis and point of projection as origin. And since this is a case of a two-dimensional motion, so our vertical direction will be treated as y-axis. So we know that the ball will travel along some path like this, and it will again strike the ground at some distance. Let the ball passes through point P after time t. So at t, it passes through point P, and let us assume its velocity is v, and it makes an angle alpha with the horizontal direction or x-axis, whatever we say. So if we resolve the velocity, the initial velocity along the two axes, we will get ux is equal to u of cos theta. Similarly, this will be u cos theta, and similarly uy uy is equal to u of sine theta. And we have acceleration due to gravity in the vertically downward direction, that is along the negative y-axis. So g is acting downwards. So a of y, that is component of acceleration along the y-axis, is minus of g because it is acting downwards along the negative y-axis. Whereas we don't have any acceleration along the horizontal axis, so ax will be 0, because if you resolve the acceleration along the horizontal direction, its component will be z of cos 90 degree, which is equal to 0. So we don't have any acceleration along the x-axis. Now coming at point P, so at point P, if you resolve the velocity along x and y directions, so Vx will be V of cos alpha and velocity along y-axis will be Vi, that is V of sine alpha. So applying the equation of motion, we can see Vx is equal to ux plus ax into t, which is equal to V of cos alpha. Ux is u of cos theta. Ax is 0 because we don't have any acceleration along x-axis, and t is the time. So we can see V of cos alpha is equal to u of cos theta. This is our first equation, and through this equation we can see the horizontal velocity of the projectile remains constant during its due course of motion. So horizontal velocity never changes because we don't have any acceleration along that direction, and which is also obvious from here. Now looking at the y component of velocity, that is the Vy is equal to u of y plus ay into t. Ay is the y component of the acceleration, which is minus g. So this implies V of sine alpha is equal to u of sine theta, because uy is equal to u sine theta, and ay is equal to minus of g, and t is the time. So you can see there are changes in the y component of the velocity during the motion of the projectile. So if you will squaring 1 and 2, and adding, we get, so first V square cos square alpha plus v square sin square alpha. This is our left hand side. On the right hand side we have u square cos square theta plus u square sin square theta plus g square t square minus of 2 u sin theta into gt. So on the left hand side we have v square. On the right hand side we have u square plus g square t square minus of 2 u sin theta into gt. So this is our third equation. Now the direction of velocity at point P, which we assumed as alpha, we can also see from 1 and 2 that tan of alpha is equal to v sin alpha by v cos alpha. This is equal to u of sin theta minus gt upon u of cos theta. So this will be our fourth equation, and this gives you the direction of velocity at any time t. So if we take some illustrative examples, if we take an illustrative example to clear that how we are going to use these equations, we can see. So our problem is a projectile is projected at an angle 60 degree with horizontal with velocity 20 meter per second. Now we have to find that at what time it will make an angle of 45 degree, at what time its angle is 45 degree with horizontal, and second, at what time it makes an angle of 90 degree with initial velocity, that is the projectile velocity, initial velocity, that is the velocity with which we projected our projectile. So we will use our basic understanding to deal with this problem. So, as you already noticed, that tan of alpha is equal to v of y by v of x, which is u sin theta minus gt by u of cos theta. So since in the first case the angle is 45 degree, so tan of 45 is equal to u is 20 meter per second and theta is 60 degree. We will consider g as 10 and t we have to find, so we will consider it as same t, and in the denominator we have u, which is 20 meter per second, and we have cos of 60 degree. So when you will solve, you will see tan of 45 is 1, sine of 60 degree is root 3 by 2 minus 10 into t upon 20, and cos of 60 is 1 by 2. So this will be 10, this will be 10, so 1 is equal to 10 root 3 minus 10t upon 10. This is 1. So you can see 10t is equal to 10 root 3 minus of 10. So we can directly cancel 10 here itself. So no need to carry the baggage of 10. So t is equal to root 3 minus 1 second. So this is the time after the projection of this much time, the velocity, the direction of the projectile will be 45 degree with the horizontal. So this is our first part. Moving to the second part, which is a bit tricky. So we will draw the motion, a schematic for the motion. This is u, this is theta. So it will follow a parabolic path, and you can see we have to find the time when the velocity of the projectile becomes perpendicular to its initial velocity. So suppose t be the time after which the velocity becomes 90 degree to the initial velocity. So if we draw a horizontal line parallel to the x-axis, you can see this is 60 degree. So this will be also 60 degree, 60, 90, and this will be 30 degree. So this will be also 30 degree. So alpha becomes minus of 30 degree because it is below the horizontal axis. So if we apply the equation, tan of alpha is equal to u sin theta minus gt by u cos theta, we can get the required time. So tan of minus 30 degree, u is 20, sin 60 minus 10 into t, 20 cos of 60 degree. Tan of 30 will be minus 1 by root 3, 20 into root 3 by 2 minus 10t upon 20 into 1 by 2. So this will be 10, this will be 10, so we can cancel the 10. So this is equal to minus 1 by root 3 is equal to root 3 minus t, and from here you can see t is equal to root 3 plus 1 by root 3, which you can write as three plus 1 by root 3, that is 4 by root 3 seconds. So after 4 by root 3 seconds, the velocity of the projectile will be perpendicular to its initial velocity. So you can see how useful the equations are that we have already derived earlier. So now moving to the last part of our discussion, we will now analyze the coordinate of the projectile so that we have the complete understanding of this topic. So in the last part, we will take our usual notations and complete our discussions. So now, coordinates of the projectile. Coordinates of the projectile. So we have our usual references for the horizontal direction and vertical direction. So this is our point of projection, that is origin. We projected a projectile. It follows the parabolic path, and u is our initial velocity of projection, theta is the direction with the horizontal axis, and after time t it passes through point P whose coordinates are x and y. So this is y and this is x. So from our earlier discussion we know that horizontal velocity is responsible for the variation in x coordinate, and we know that horizontal velocity is constant. So at time t it passes through point P, so x can be written as u cos theta into t. So this is our first equation, and you can see that x and t have linear relationship. I mean, if you draw the graph between x and t, you will get a straight line like this. So this is your x and this is your t. So your graph will be like this, passing through the horizon. Similarly, Y component of velocity is responsible for changes in y coordinates, so y can be written as u sine theta into t minus half gt square. This is our equation 2, and from this equation which you can see we have quadratic equation between y and t. So for each y we have two values of t. For example, at time t equal to 0, y is equal to 0, and after completing the motion y is also equal to 0. And suppose capital T be the total time of flight of the projectile. So after capital T, y is equal to 0. So y is equal to 0 at the two instant of time, that is initially and finally when it strikes the ground. So let t is equal to total time of flight of the projectile. So if we put, we will get y is equal to 0, u sine theta into t minus half gt square. So neglecting the t equal to 0, we will get t is equal to 2 into u sine theta by g. So this is your total time of flight. If you put this value of t in equation 1, you will get the value of x when the projectile strikes the ground after its projection. So this we generally call as the range of the projectile, which we usually denote by capital R. So range of projectile R is equal to u cos theta into t, u cos theta into capital T, and capital T is equal to u cos theta into 2u sin theta by g. Therefore, R can be written as 2u square cos theta sin theta by g. And from trigonometry we have a relation that sine of 2 theta is equal to 2 sin theta cos theta. So we can write u square sin theta, u square sin 2 theta by g. So this is our relation for range. You can see that sin theta is maximum when sin 2 theta is maximum when it is equal to 1. I mean, the maximum value of sin 2 theta is 1, and it is maximum when 2 of theta is equal to 90 degree. This implies theta is equal to 45 degree. I mean 90 by 2, 90 degree by 2, which is equal to 45 degree. So if you project a projectile at an angle of 45 degree with the horizontal, with the velocity we have, it will have the maximum change in x direction if you project it at 45 degree with the horizontal. So now we will calculate the relation between x and y. So if we substitute the value of t from equation 1 in equation 2, you can see y is equal to u sine theta into t. From here, t is equal to x by u cos theta. So I am substituting the t by u cos theta minus half g t by u cos theta whole square. So this implies y is equal to, u will get cancelled, so t tan theta minus half g t square u square cos square theta. This is our equation 4a. Sorry, I missed something. Just a moment. So we are actually substituting, take my pardon, we are actually substituting x. So here it will be x and here it will be x. So here it is x. So from equation 4a you can see theta is constant, g is well known constant, u is the velocity of projection which is also constant, and cos square theta is also constant. So except x and y, every term is constant. So it's a quadratic equation in x and y, and this proves that the relation between x and y is parabolic, and that is why we generally call that the projectile follow a parabolic motion. Now from this relation you can see r is equal to u square sine 2 theta by g. So we can also write it as r by sine 2 theta equal to u square by g. You can substitute this value in equation 4a. So substituting the value of u square by g in equation 4a, we get y is equal to x tan theta minus half x square by u square g cos square theta. U square by g can be replaced by u by r by sine 2 theta. So y is equal to x tan theta minus half x square by r sine of 2 theta. In the denominator we have cos square theta. So if you simplify, x tan theta minus half x square by r And from the relation we have already used, sine 2 theta can be written as 2 sine theta into cos theta upon cos square theta. So you can cancel one cos theta from numerator and denominator, and we will get this is equal to x tan theta minus 1 by 2 x square by r. 1, 2 we can cancel, so no need to carry half. So x square by r and sine theta upon cos theta, that will be tan theta. So if we take tan theta out, which is a constant, x minus x square by r. So this is our equation 4b. So we can use either of the equation, either 4a or 4b, to say that the path of the projectile is parabolic. So this is the complete basic analysis of the projectile motion. Hope you find it very useful for you. See you. Thanks.